Have you ever gazed up at the night sky and wondered how many alien civilizations might exist in our galaxy? This is the great cosmic mystery that has captivated human imagination for centuries. We've looked to the stars with a mix of awe and curiosity, driven by an insatiable need to know, are we alone in this vast universe? From ancient philosophers to modern scientists, we've always sought answers. Today, with the help of cutting-edge technology and scientific models, we're closer than ever before to unraveling this mystery. Telescopes peer into the distant cosmos, spacecrafts venture to the far reaches of our solar system, and researchers tirelessly analyze the data, all in the pursuit of extraterrestrial life. But how do we quantify something as elusive as the existence of alien civilizations? How do we begin to estimate such a number? Today we explore one of the most intriguing tools in this quest, the Drake equation. Developed in 1961 by astronomer Frank Drake, the Drake equation is not just a formula, but a roadmap to understanding the universe's communicative civilizations. The Drake equation, in essence, is a probabilistic argument that attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a fascinating tool, a scientific compass of sorts, guiding us in our search for intelligent life beyond our own planet Earth. So what makes this equation so special? Well, it's the way it breaks down a complex question into manageable pieces. The equation doesn't dive straight into the science fiction-like quest to find alien life. Instead, it systematically takes into consideration various factors that would contribute to the existence of such civilizations. It begins with the rate of star formation in our galaxy. It then considers the fraction of those stars that have planetary systems and the number of planets that could potentially support life as we know it. The equation factors in the fraction of planets where life actually develops, and then narrows it down further to consider on how many of those life could evolve to become intelligent. It contemplates the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And finally, it ponders the length of time such civilizations can communicate. The beauty of the Drake equation is not in its precision, but in its approach. It offers us a systematic way to organize our ignorance, to break down a seemingly insurmountable question into a set of smaller, more manageable questions. It's a tool that stimulates scientific dialogue, spurring us to seek answers, to explore the unknown, to look up at the stars and wonder, are we alone? The Drake equation, in its simplicity, is a symbol of our collective curiosity, a testament to our quest for understanding, a beacon in our search for extraterrestrial intelligence. Now let's delve deeper and decode each factor of this fascinating equation. The Drake equation consists of several factors, each representing a crucial element in the quest for alien life. Let's delve into these factors one by one. Our first factor is the average rate of star formation in our galaxy. This is the birth rate of stars, if you will. You see, stars are the cosmic cradles where planets form and potentially life begins. So the more stars there are, the higher the chances of planets, and hence, life. Moving on, our second factor is the fraction of those stars that have planets. Not every star has a planetary system, but many do. And the more stars with planets there are, the better our odds of finding life. So this factor is crucial in our cosmic quest. Our third factor is the average number of planets that could potentially support life per star that has planets. This is not just about planets, but about planets that are in the Goldilocks zone. This zone is just right, not too hot, not too cold. That liquid water, an essential ingredient for life as we know it, could exist. Next, we have the fraction of planets that could support life that actually develop life at some point. The conditions might be right, but that doesn't guarantee life will emerge. This factor considers those planets where the magic of life has sparked. The fifth factor is the fraction of planets with life that actually go on to develop intelligent life. This is where things get really interesting. We're not just talking about microbes or simple organisms anymore, but civilizations, societies, beings that can ponder their own existence. The sixth factor is the fraction of civilizations that develop technology that releases detectable signs of their existence into space. This is about civilizations that have reached a level of technological advancement where they can, intentionally or unintentionally, broadcast their presence to the cosmos. Think about our own radio and television signals reaching out into the void. Finally, the seventh factor is the length of time such civilizations release detectable signals into space. This is a measure of longevity. How long can a civilization sustain this level of technological output? This could be a blink of an eye in cosmic terms, or it could span millennia. Each factor combines to give us a speculative, but scientifically grounded estimate. The Drake equation is not a definitive answer, but a sophisticated tool that helps us explore one of the biggest questions we can ask. Are we alone in the universe? While the Drake equation provides a framework, it's not without its controversies and complexities. This mathematical formula, as elegant as it is, has its fair share of challenges and limitations. First and foremost, there are huge uncertainties in estimating each factor. It's like trying to solve a jigsaw puzzle with pieces that are constantly changing shape. Take, for instance, the factor for the average rate of star formation in our galaxy. Scientists can't precisely pin down this number because it varies over time. And then, there's the factor for the fraction of planets that could support life. This is a real head-scratcher because it depends on our understanding of what constitutes a habitable zone. Even if we could accurately estimate all these factors, we're still left with the big question. How many of these life-supporting planets have actually given birth to civilizations advanced enough to communicate with us? This is where things get really tricky. After all, we only have one example of a civilization so far, ours. So, it's like trying to predict the outcome of a lottery based on just one winning ticket. But here's the thing. The Drake equation isn't just a tool for estimating the number of alien civilizations, it's also a mirror that reflects our ever-evolving understanding of the cosmos. With each new discovery, the estimates can change. For example, the discovery of exoplanets, planets orbiting stars outside our solar system, has potentially increased the number of places where life might exist. And then there are the philosophical implications of the equation. It forces us to confront the possibility that we might not be alone in the universe. That's a mind-boggling thought, isn't it? It challenges our notions of life, existence, and our place in the cosmos. Despite its uncertainties, the Drake equation continues to fuel both scientific research and public imagination. It's a beacon guiding us on our quest to answer one of humanity's oldest questions. Are we alone in the universe? Whether we find the answer or not, the journey itself is an adventure worth embarking on. From radio signals to space telescopes, our search for alien life is more vibrant than ever. We have come a long way from merely gazing at the stars and wondering. Today, our pursuit of understanding whether we are alone in this vast cosmos spans across a multitude of disciplines and technologies. Take, for instance, SETI, the search for extraterrestrial intelligence. This robust program is on a relentless quest, scanning the universe for signals that might be the handiwork of intelligent alien life. SETI's approach is grounded in the belief that any advanced civilization would likely harness the power of radio waves, just like us. But that's not all. We've also got the Kepler Space Telescope, an observatory in space that's on a mission to find Earth-like planets. Kepler's discoveries have been monumental, opening our eyes to the sheer number of planets that could potentially host life. It has given us a better understanding of the NE, the average number of planets that might support life per star, a crucial factor in the Drake equation. And let's not forget the James Webb Space Telescope, the successor to Hubble. This marvel of technology, with its superior ability to gaze into the universe's distant past, could help us refine the FL, the fraction of those planets where life actually develops. Every stride we make in technology, every planet we discover, and every signal we analyze brings us one step closer to answering that profound question. Are we alone? These efforts not only help us refine the factors of the Drake equation, but they also remind us of our place in the universe. They remind us of the vastness of space and the possibilities that lie within it. As we refine our tools and expand our knowledge, the mystery of whether we are alone in the universe remains one of the most profound questions. A question that perhaps we may be closer to answering than we ever thought possible. The universe is vast and its mysteries are profound. As we journeyed through the Drake equation, we've seen how this mathematical formula provides a roadmap, a way to estimate the number of advanced civilizations that might exist in our galaxy. It's a fascinating blend of astronomy, biology, and probability, revealing that even the most conservative estimates suggest we're not alone. But it's important to remember that the Drake equation is not a crystal ball. It's a tool for sparking curiosity, for igniting scientific inquiry. The real answers lie in the cosmos, waiting for us to discover them. The search for alien civilizations continues, propelled by our insatiable curiosity and our unwavering hope. We may not know what lies beyond our celestial neighborhood, but our quest for knowledge drives us forward. Whether we find other civilizations or not, the journey of discovery reshapes our place in the cosmos. Keep looking up, keep wondering.